Morning, here today with Doc Kupo and Doc Reyes. We'll be understanding VSEPR theory in molecular geometry. Let's get started.
So first off for the definition, valence shell electron pair repulsion theory is a fundamental model in chemistry that predicts the three-dimensional shape of molecules based on the repulsion between electron pairs surrounding the central atom. The theory is built on the principle that electron pairs, whether in bonds or as lone pairs, repel each other and strive to be as far as possible to minimize the repulsion. This arrangement determines the molecular geometry and bond angles of a molecule. By applying VSEPR theory, chemists can predict molecule shapes, which are crucial for understanding chemical reactivity, polarity, and interactions with other molecules. Molecular geometry plays a significant role in determining a compound's physical properties, biological activity, and its behavior in chemical reactions. And here we show examples of that in the pictures. Now are the key concepts which we're going to be discussing about. The first one is electron domains, the second bonding pairs, the third lone pairs, the fourth bond angles, and the fifth molecular shapes. Now Loic will explain these to you.
Electronic domain. Electronic domain refers to the regions around the central atom where electrons are likely to be found. These can include both bonding pairs and lone pairs. The number of electron domain influences the overall shape of a molecule as they repel each other and adjust spatially and minimize repulsion.
Bonding pairs. Bonding pairs are valence electrons that are shaped between two atoms to form a covalent bond. These pairs hold atoms together in molecules and play a key role in determining molecular geometry. The number of bonding pairs around the central atom affect bond angles and the overall molecular shape and structure.
Lone pairs. Lone pairs, also called non-bonding pairs, are pairs of valence electrons that do not participate in bonding but still influence molecular shape. Because lone pairs occupy space and exert repulsive forces on bonding pairs, they can alter bond angles, leading to deviations from idealized molecular geometry. Lone pairs are especially significant in bent and trigonal pyramidal shapes. Here are some examples on the side.
Now the bond angles. Bond angles refer to the angles formed between two adjacent bonds in a molecule. These angles are determined by the number of electron domains and the repulsion between bonding and non-bonding pairs. Different molecule structures and shapes have characteristic bond angles such as 180 degrees for linear molecules, 120 degrees for trigonal planar molecules, and 109.5 degrees for tetrahedral molecules.
Molecular shapes. Molecular shapes is a three-dimensional arrangement of atoms in a molecule. It is determined by the number of electron domains and how they distribute themselves to minimize repulsion. Molecular shape affects many properties of a substance, including polarity, reactivity, and intermolecular interactions. Here are some examples of them on the side.
Now we're going to start off with the molecular geometries. Linear. Linear molecule shape occurs when there are two electron domains around the central atom. The electron pairs align at an angle of 180 degrees to minimize repulsion. Trigonal panel. Trigonal planar shape is observed when a molecule has three electron domains with no lone pairs. The atoms form a triangular shape around the central atom with bond angles of 120 degrees as shown in the image below.
Okay, the two other ones are tetrahedral. The tetrahedral shape occurs when three or four electron domains around the central atom are occupied by bonding pairs. This arrangement results in bond angles of 109.5 degrees to minimize repulsion, as you can see on the bottom. Bent molecular shape arises when a molecule has four electrons domains but two or lone pairs, as you can see on the example on the bottom.
Final two, trigonal bipyramidal. In trigonal bipyramidal shape, a molecule has 5 electron domains with bond angles of 90 degrees and 120 degrees. This results in a 3-dimensional structure where 3 atoms form a equatorial plane and 2 atoms are positioned above and below it. Octahedral. Octahedral shape occurs when a molecule has 6 bonding pairs and no lone pairs, resulting in a bond angle of 90 degrees. The central atom is surrounded symmetrically by 6 atoms in a 3-dimensional shape, as shown in both of these images right here.
Okay, here are some examples of molecular geometries. First example is linear, 180 degrees. An example of this is carbon dioxide, CO2. The explanation: CO2 has a central carbon atom with 2 double bonds to oxygen, so the shape is linear, as you can see on the example on the bottom. The another one is trigonal planar, 120 degrees. An example of this is boron trifluoride, BF3. Explanation: boron trifluoride has 3 bonding pairs and no linear pairs, forming a trigonal planar shape. Tetrahedral, 109.5 degrees. An example of this is methane, CH4. CH4 has a central carbon atom with 4 bonding pairs to hydrogen atoms. These electron pairs arrange themselves as far apart as possible, forming a tetrahedral shape with 109.5 degrees bond angles, as you can see in the examples on the bottom.
Now the example of Ben. The example of it is water, which is also H2O. H2O has 2 bonding pairs and 2 lone pairs on the oxygen atom. The lone pairs exert greater repulsion than bonding pairs, compressing the bond angle below 109.5 degrees and forming a bent shape. Bipyramidal, 90 degrees and 120 degrees. An example of this is PCI5. PCI5 has 5 bonding pairs and no lone pairs around phosphorus. The electron pairs arrange themselves into a trigonal bipyramid shape with 3 equatorial bonds at 120 degrees and 2 axial bonds at 90 degrees. An example of this is sulfur hexafluoride, which is also known as CF6. CF6 has 6 bonding pairs around sulfur. These pairs spread out evenly, forming an octahedral shape with all bond angles at 90 degrees, which is shown here in the image.
This is our works cited where we find all the information. Thank you for
listening
to our very good presentation.
You guys took a good understanding on our topic, and we can't wait to teach you guys more.
If any questions are needed, let us know. Thank you.